In this section, we'll discuss maxima and minima of a function. This is probably one of the most versatile uses of the derivative in various applications. It can be used in business, in physics, in any scenario where you have some relationship and you want to know what is the largest value, what is the smallest value, which is a fairly common question one asks. So first, let's post up our definition. Just start with let C be a real number in the domain D of F. Then F has a maxima at C if F of C is bigger than F of A for everybody in the domain, and we'll call that a maximum value. Alternatively, or vice versa, F will have a minimum at C if F of C is smaller than every other value of F in the domain. In this case, we say that the F of C is called the minimum value of F. So there are several scenarios that can occur with any function. It could have one maximum, many maximum, one minimum, many minimum. It could have or no maximum or minimum. Let's look at a couple of examples here. So we could have a function like 1 over x. So y is 1 over x, and its graph looks like something like this. And we see that it has no maximum because as it approaches the y-axis, it goes off to infinity, and it has no minimum value. It does have an asymptote getting closer and closer to 0, but it never reaches 0. So this would be an example of no maximum or no minimum. We could also have the example of maybe a parabola, and say it looks something like this. And then we see that there is a maximum value that occurs here. And if our domain, say, maybe this is minus 4 to 4, so if we're on a closed domain, we would have a minimum value of 0 at these locations. So this is an example where we have one maxima and two locations where we have a minimum value, though it's the same minimum, right? It's 0. And a third example, maybe like a sine function, which looks, maybe something like this looks like a negative cosine function, but nonetheless, some kind of trig function that looks, say, something like that. And we see that we've got maximum values here, a maximum value here, which would be the value of 1. And then we've got minimum values here and minimum values here. Both of those, say, would be negative 1. And something I really want to note that, like in this example with the parabola where we had two locations where we had a minimum value, or in the sine function where we had multiple cases where we had max and multiple locations of min, the minimum value of the function or the maximum value of the function in either case was the same number. And that kind of makes sense based on the definition, because let's say F has a maximum at x equals c1 and when x equals c2. Well, by being a maximum, we know that f of c1 is bigger than every evaluation in the domain, including it's going to have to be bigger than or equal to f of c2. But for identical reasons, f of c2 would have to be bigger than or equal to f of c1. well, put those together, the only way two numbers can be bigger than or equal to both of each other means that they both have to be equal. So f of C1 has to be equal to f of C2. So we see that maximum values of a function are unique. By a similar argument, minimum values of a function have to be unique. So the question here is, how do we find these minimum value? How do we find the spots, C1, C2? In this case, how would we find where this minimum value is? Now, granted, we can, in these cases, we can kind of look at the graph and know some things about the function to determine, but we'd like to use calculus to find those spots where we have a max or a min. So here we give a theorem called the critical point theorem, which says, let f have a domain, and let's suppose C is some point in the domain where f either has a maximum or a minimum value. Then one of the following three things must be true. Either 1, C is an endpoint of our domain. 2, the derivative at C is equal to 0. Or 3, the derivative at C does not exist. If any of these three things are true, we shall say that C is a critical point of F. So let's look at these three scenarios. So scenario 1, we have that our endpoints are critical values. And so let's say here, this is our endpoint maybe A, and this is our endpoint B of our domain, and maybe our function is like a straight line in which it is the smallest value occurs here at the endpoint, and the largest value occurs here at the endpoint. So that's one scenario that could happen. The second scenario would be where the derivative is 0. So again, let's look at our endpoint here is A of our domain, our other endpoint here B in our domain, and maybe our function goes up for a little bit, comes back down, and then comes back up again. Well, we see that we have a minimum here, or sorry, maximum there, and a minimum here. Well, at the maximum, what is the slope of our curve? Well, the slope is going to be straight as that could be, is a straight line, right? So the slope here, would be 0. Similarly, down here at our minimum value, if we look at the slope of our curve, it's going to be 0 as well. So in both scenarios, we see that the derivative, since the slope of the curve there is 0 and the slope of the curve there is 0, our derivative would be 0. So that's case 2. And then the third case would be where maybe the derivative doesn't exist. Again, let's look at our endpoints, A and B, and kind of like the last graph, but we'll put some hard angles. And then we see again, here at the top is our maximum. This is our maximum value, and this is our minimum value. And in both cases, because we've got a sharp cusp there, the derivative doesn't exist. So those are the three scenarios that can happen in in which we have a maximum or a minimum. So this limits our scope of what we need to look for. If we're trying to find locations of a max or minimum, then we just have to either look at the endpoints or look where the derivative is 0 or does not exist. And again, we'll call any of those three scenarios a critical point. So really, the hunt for locations of max and min become a hunt for critical points. And these are things that we can get at just directly through analysis using calculus. So let me put up here the direct test for determining, once we have a critical value, how can we find out, is it a max, a min, or neither? So let's suppose that C is the set of all critical points of F. So they're all the set, so it's the set of C such that either C is an endpoint, the derivative at C is 0, or the derivative doesn't exist. Remember, that's what a critical point is. So let's suppose that C is the set of all critical points of F in the domain. Then, if F of C is bigger than all the other valuations of F on the critical points, then we know that F of C is a maximum value of F. On the other hand, if F of C is smaller than the evaluation of F on all the critical points of C, then it's a minimum. And otherwise, it's neither a max or a min. So let's consider the example where f of x is negative x squared plus 4. And we'll let our domain be the closed interval from -2 to 2. Now, this is a simple enough problem. We could graph this and probably see. In fact, actually, my college algebra students could tell me where the maximum value of this function is because it'll happen at the vertex. But nonetheless, it's a good example. It's a starter for us to, again, just kind of see how do we use the direct test. So we need to find all the critical values. So first off, -2 and 2 are going to be critical values because they're endpoints. So right off the bat, I know that my set of critical values, so C, will have at least -2 and 2 as members of my critical values. Now, there could be some others. There could be places where the derivative is 0 or the derivative doesn't exist. So let's look at the derivative. So f prime of x is equal to -2x. And we want to know when is it 0. Right? We want to know when is the derivative 0 or when does it not exist. Well, -2x exists everywhere. So there's nowhere where it fails to exist. But we can ask the question, when is it 0? And it's 0 when x is 0. So we can add that to our set of critical points. We'll put that in this set. So 0 is also in here. And that is all of our critical values, endpoints and places where the derivative is 0. So now, how do we use the direct test? We found our critical values. And the direct test says, well, we just have to evaluate the function at all the critical points to see where the maximum values are. So I'll make a table over here. We'll put our points in C here, and we'll evaluate F over here. So we've got, say, -2, 2, and 0. And when we put -2 into F, now, I'll just forewarn you, a common mistake students do when they're not maybe quite thinking things through all the way, that they'll put these values into f prime. That is not where it goes. We need to put these values into f, right? So we need to take -2 and put it into f right here. So this would be f of -2, which would be equal to -2 squared plus 4, which is 0. Similarly, if we put 2 into there, the answer would be 0. And then if we put 0 into our function, our answer would be 4. So look what we've got. That we just have to evaluate the function on the critical points. That's what we've done. And now we just need to compare. Which is the largest? Well, 4 is the max value of our function because that is bigger, obviously, than 0. And then 0 is our minimum value. And this should make sense. If I were to draw the graph, it would look something like a parabola. The max here is at the point 0, 4, and the minimum value would be here at -2, or actually +2, 0, and at -2, 0. So the direct test, we didn't have to graph it. We didn't have to know really anything about the function. We just had to know what are the critical points for it. And the critical points are either when the derivative is 0, when the derivative doesn't exist, or the endpoints.